Hello everyone, my name is Isai Kumar and I am from ECE D section. My topic is a new signal representation using complex conjugate pair sums. Let us see the introduction. Finite length signal representation is a fundamental concept in signal processing which has been studied for years. There are some techniques like DFT, DCT, discrete cosine transform, and RPT. Here DFT and DCT are very well known techniques, whereas RPT is newly introduced by P.P. Vaidyananth, which is widely used in period estimation applications. Recently, Srikanth V. Tenetti and P.P. Vaidyanathan introduced a specific kind of signal representation using nested periodic matrices (NPMs), which is useful for periodic estimation. RPT and DFT are members of NPM's family. The signal representation proposed in this letter is inspired from NPMs and subspace based signal representation. For a given positive integer n is greater than or equal to 3, there exist two pair of complex conjugate exponential sequences having period exactly equal to n. By using each pair, a real valued summation known as complex conjugate pair sum is introduced. Later, some of its properties like symmetricity, periodicity, and orthogonality are studied. It is shown that each proposed summation and its one circular downshift act as a basis for two-dimensional complex conjugate subspace. So, there are total two complex conjugate pair sums leading to phi of two complex conjugate subspaces for a given positive integer n is greater than or equal to 3. Utilizing the orthogonality property of complex conjugate pair sums, it is proved that any two complex conjugate subspaces are mutually orthogonal. Then the direct sum of all these psi of two complex conjugate subspaces forms a psi of n dimensional subspace n. We solve the problem of signal representation by considering the signals from divisor subspaces P as Ds since d by n phi of d equal to n. Complex conjugate pair sum. In DFT, an n-finite length signal is represented by using the following complex exponential basis: s of n comma s of n, Sn comma k of n is equal to e power j 2 pi kn into n. For a given k, we denote the period Sn comma k of n by pk. It is known that pk equal to n of k comma n. Hence, in order to count the number of k, k belongs to 0 comma 1 comma so on to n minus 1, having a particular period d belongs to dn, it is sufficient to count the number of